Two laboratory tests that are widely used for both development and evaluation of lubricating fluids are the American Society for Testing and Materials, or ASTM, D-4742, Thin Film Oxygen Uptake Test, or TFOUT, and the ASTM D-2272 Rotating Bomb Oxidation Test, RBOT. Both tests use the same apparatus to measure the lubricant's ability to resist oxidation. Only the applications differ. The apparatus is comprised of a cylinder or bomb, which contains a test jar filled with the lubricant as well as the catalyst. A catalyst consists of all the properties and elements that may be present in real-life conditions. The bomb is then sealed, pressurized with oxygen, placed in a heated oil bath, and rotated at 100 RPM. For the RBOT ASTM D-2272 test, the catalyst will be copper and water. A prepared sample consisting of 50 grams of the oil to be tested, 5 milliliters of water, and the copper catalyst is placed in the bomb, which is then pressurized to 90 psi with oxygen, immersed in a hot oil bath set at 150 degrees Celsius, and rotated at 100 RPM. The purpose of this test is to simulate the aggressive degradation faced by gearboxes, differentials, transmissions, and power steering units in everyday service. For the TFOUT test, the catalysts represent different metals as well as degraded fuel and antifreeze contamination. A prepared sample consisting of 1.5 grams of the oil to be tested and the test catalysts is placed in a bomb which is pressurized to 90 psi with oxygen. The bomb is then placed in a hot oil bath at 160 degrees Celsius and rotated at 100 RPM. A laboratory test commonly used to determine the low temperature operability of distillate fuels such as automotive diesel fuels and gas oils, including those containing a flow improving additive, is the cold filter plugging point, CFPP, test method IP-309. The CFPP is defined as the lowest temperature expressed as a multiple of 2 degrees Fahrenheit, at which the fuel, when cooled under prescribed conditions, either will not flow through the filter or requires more than 60 seconds for 20 milliliters to pass through the filter. The apparatus consists of a test jar, filtering pipette, vacuum supply, thermometer, and a methanol cooling bath. The fuel sample is filtered, .45 milliliters is added to the test jar, and the test jar is closed. The pipette is attached to a filter unit that houses a 45-micron fine wire mesh filter. The test jar is then placed into the methanol bath maintained at a temperature of -51 degrees Celsius. A controlled vacuum is applied so that the fuel sample will flow up through the filter into the pipette. A stopwatch is used to time the flow of the fuel from the time the vacuum is applied until the fuel reaches an etched mark on the pipette. The sample is tested every 2 degrees Fahrenheit as it cools until the fuel fails to reach the etched mark within 60 seconds. At this point, the filter is considered plugged and the temperature is recorded. A lab test used for development and analysis of lubricating oils is the ASTM D-445 Kinematic Viscosity of Transparent and Opaque Liquids. The apparatus consists of a temperature-controlled bath, a viscometer, and a stopwatch. The viscometer is filled with the oil to be tested and placed into the temperature-controlled bath. Each viscometer is marked with a top and bottom mark. Once the temperature of the sample has reached equilibrium with the bath, a vacuum is applied to the viscometer to raise the fluid above the top mark. The vacuum is removed, and the fluid is allowed to flow freely down the viscometer. A stopwatch is used to measure the time it takes for the fluid to flow from the top mark to the bottom mark of the viscometer. The viscosity is then calculated by multiplying the measured flow time and the calibration constant of the viscometer. An instrument commonly used in research and quality control is the infrared spectrophotometer. The IR utilizes an infrared source and a spectrophotometer to produce a spectra. The peaks and valleys of the spectra are as unique to a chemical compound as a fingerprint is to a person. The sample is placed on the IR crystal and the scan is performed. Once the spectra is obtained, a computer database of IR spectral libraries can be searched to find the best match in which to compare it. The library can be added to as new raw materials, chemical compounds, and industry-related products become available. The IR can be extremely helpful in quality control analysis and wear trend plus analysis when comparing spectra to known standards. Wear trend plus analysis is comprised of several different tests to analyze the different parameters of lubricating oil. Viscosity, oxidation, nitration, and wear metal contamination are all important when trying to determine drain intervals and maintenance schedules. The viscosity of the used oil is analyzed to see if it is still in the required viscosity range for the equipment. A viscosity that is too low or too high will not lubricate properly and can be indicative of fuel dilution or glycol contamination. Infrared spectroscopy is used for determining the oxidation and nitration level of the oil, as well as any fuel, water, or glycol contamination. The sample is then analyzed by inductively coupled plasma, ICP, for wear metals and additive concentration. As various parts of the engine, transmission, or gearbox begin to wear, the metal that makes up these parts is left in the oil. The ICP can detect these wear metals, as well as components of antifreeze and dirt in the parts per million range. As the used oil is sampled and analyzed at different intervals, a trend for wear can be established. This trend allows the owner of the equipment to save time and money in premature oil changes. The various components of the equipment can also be monitored for wear, and maintenance repairs can be made before a failure occurs.